Welcome to my YouTube channel. In this video lecture, I am going to solve all the questions from Keith Williams' radio navigation book. The name of the chapter is Radar Theory. This chapter basically deals with the basic fundamentals of primary radar. When we do this chapter and answer all the questions, all our concepts will be revised and concepts will get cleared. And when we are confident in this chapter, we will continue to the next chapter, which are applications of radar theory, primary radar, secondary radar, DME, airborne weather radar, like that. So let's begin with question number 1 from this chapter. The question number 1 is, the minimum range of a primary radar using the pulse technique is determined by what and maximum range is determined by what factor? Very important question, okay, for CPL and ATPL, very important. So this is a direct fact. It's given in the textbook also in the chapter. The minimum range of a primary radar is determined by pulse length and the maximum unambiguous range is determined by pulse recurrence frequency. So option number 1 is correct. So minimum range of a primary radar is pulse length. Maximum unambiguous range is by the pulse recurrence frequency. So remember, let's say this is your transmitter. Okay. So the maximum range, and there is your aircraft. So the maximum range is directly proportional to the pulse recurrence frequency. Okay. Is inversely proportional to pulse recurrence frequency. If we want to have more range, the frequency should be little. If we want to have short maximum range, the frequency should be more. What is the concept? The pulse should originate and reach the target and get reflected from the target and received back at the transmitter. Okay, so let's say there is number 1 pulse. This pulse will originate from the transmitter. Then it has to go to the target, strike the target, and then come back at the transmitter from where it originated. After this complete journey of the first pulse, the second pulse will be sent. Okay, so this is your pulse number 1. After this, the second pulse, let's say this is your second pulse, that will be sent. It will go to the target, strike the target, get reflected and come back. Okay, so first, only when the first pulse has gone to the target and come back, the second pulse will be generated and it will be sent to the target. If this doesn't happen, just before your pulse number 1, that is this red color pulse, goes to the target and comes back, okay, while that process is going on, if you send another pulse, the second pulse, so this second pulse will also go to the target and come back, maybe at the same time, maybe a few microseconds later. So what happens is the ATC radar controller will not be able to determine the pulse, okay, will not be able to determine the pulse with the target. Whether the target that ATC sees on his radar screen belongs to number 1 pulse, the pulse which was sent previously, or the pulse which was sent later. So to avoid this, or to avoid this confusion, okay, ambiguity, we send radar pulses turn by turn. Once the entire pulse has gone and come back, we send the next pulse. So this is called pulse recurrence frequency. The number of pulses that you are sending per second. Okay, pulse recurrence frequency is number of pulses sent every second. So maximum range is inversely proportional to pulse recurrence frequency. If we want maximum range, okay, large maximum range, the frequency should be little, very little. Okay, that means the number of pulses that you are sending every second are very small in number. If the maximum range required by you is not that great, the pulses you sending that you are going to send every second is going to be a little bit more. So that's why it's inversely proportional to PRF. Next, the concept of pulse recurrence, pulse width of pulse, also known as pulse length. Now, pulse width of pulse length is the length of a pulse or the distance occupied by a pulse measured in microseconds. Measured in microseconds. So what happens? Again, there is a transmitter, okay, and there is, let's say, a target here and a target here. Now this first target is 150 meters away from the transmitter. Okay, the second target is 3 meter away from the transmitter. Now whatever pulses the transmitter sends, that pulse is 300 meter long. 1 microsecond, a 1 microsecond long pulse is equal to nothing but in distance 300 meter long. So let's say this pulse has originated from the transmitter. Okay, so this is the first pulse. Okay, that is originated from the transmitter. Now this pulse that is going to get originated will be 300 meters long. 300 meter long means this pulse will be this much long. 300 meter up to this target. Now if any target is at 150 meter, which is half the 300 meter, that means the pulse that is going to reach this target will be the half of this entire pulse width. The entire pulse width is 300 microseconds. Half of it is 150 microseconds. So if there's any target, okay, which is less than 300 meters from the transmitter, 150 meter, 200 meter, 250 meter, any value less than 300 meter, in that case, the pulse going to strike or the pulse that is going to reach the target will be less than 300 meters. Okay, if it's at 150 meter, the pulse which is going to go to the target will be half of that. If it's 200 meter, it's going to be less than 300 meters. So any value less than 300 meter. That means the pulse that is going to strike this target will be 150 meters long. Will be 150 meter long. Once it strikes the target, it will come back to the transmitter. Okay. But what will be the disadvantage of this? In order to get a blip or in order to get an indication on the ATC radar screen, the entire pulse, this entire 300 meter pulse should go to the target and then come back. Otherwise, the indication on the ATC radar screen will not be proper. So if there is any target less than 300 meter, let's say 150 meter, so the only 150 meter length of pulse will strike the target and come back. As a result, the indication given by the ATC radar screen will not be proper. Okay, so it can also happen that this radio wave will go to this target which is 300 meter long and it will come back at the transmitter. At the same time, this reflection of the radio pulse will also come back at the transmitter. So one pulse coming from 300 meter target, another pulse is coming back from 150 meter target. So these both pulses will coincide on the ATC radar screen, and the ATC radar controller will not be able to distinguish between this target and this target. So in order to get proper resolution means a proper differentiation between two targets or among many targets, we want that minimum range that any target should be from the transmitter is 300 meters. Okay, it is 300 meter. Any target less than that will have this disadvantage that the radar pulse will not fully originate from the transmitter before it strikes the target. So I'm writing it here. pulse width 1 microsecond is 300 meter long. Okay, so minimum range is determined by pulse width. Minimum range is determined by pulse width. So correct option will be option number A. Minimum range, pulse length or pulse width measured in microseconds. Pulse recurrence frequency is the maximum range. Number of pulses per second. Pulses per second. This is microsecond. So very important question for your ATPL and CPL exam. I have explained this concept in one video lecture in which I have marked important points from radar theory chapter or basic radar principles chapter from Oxford Radio Nav book. So do watch that lecture also. Mark the important points from that chapter, and while marking important points, I have also explained the concepts. Let's go to question number 2. Which of the following statements is correct concerning the use in primary radar of continuous wave transmissions as compared with pulse transmissions? Now there are two modes of transmissions, continuous wave transmission and pulse transmissions. Continuous wave transmissions, a continuous wave transmission is used in case of radio altimeter instrument. Pulse transmissions are used in case of primary radar, secondary radar, airborne weather radar, DME. Okay, so this mode of transmission is pulse. In case of radio altimeter, it is continuous wave transmission. A continuous wave transmission means that the wave, the radio wave that we are going to send, okay, it will be continuous wave, meaning that wave will be, in case of continuous wave transmission, the radio wave will be frequency modulated. The radio wave will be frequency modulated. That means the wave that you are going to transmit will be at a certain frequency. Okay, when it goes to the target, gets reflected, the frequency will shift or the frequency will change. And this change in frequency is compared to determine the distance between the transmitter and the target. In case of radio altimeter, what happens? You're going to transmit the radio wave towards the ground. Okay, radio wave towards the ground. This radio wave will be frequency modulated. So the frequency at which you're going to send will be different from the frequency being received. This difference in frequencies are compared. You know the speed of the radio wave. You can calculate time, and hence you can calculate the distance between your aircraft and the ground below you. So this is I have explained, given you in simple words the explanation. In detail, when we do radio altimeter chapter, we will understand its mechanism and principle of operation, and we will come to know about continuous wave transmissions properly in that chapter. But as of now, just remember continuous wave and pulse transmissions are used in what kind of equipments? Continuous wave transmissions means basically your radio waves are frequency modulated. One advantage of continuous wave transmission, okay, over a pulse transmission is that continuous wave transmissions do not have the requirement, okay, a requirement of minimum range. In case of pulse transmission, we saw that there is a requirement of minimum range. Okay, if the target or if the object is within that minimum range, there will be wrong reception of radar pulses. Okay, so there is a minimum range beyond which all targets should be situated, okay, from the transmitter. But in case of continuous wave transmissions, there is no such requirement. Your object or your target can be very close to you. Okay, so there is no requirement. So the advantage is that or the statement which is correct is a smaller common transmitter and receiver aerial can be used. It is less effective in short range radars but more effective in long range radars. It eliminates minimum target reception range. Equipment is required more complex in continuous wave radar, but this is offset by reliability and accuracy. So the correct option is option Charlie. In case of continuous wave transmissions, we do not have minimum target reception range. This statement is given in the very beginning of the chapter. So read the chapter carefully. Next, question 3. A primary radar operates on the principle of what? Transponder interrogation, pulse technique, phase comparison, continuous wave transmission. So answer is pulse technique. Primary radar will operate on the basis of pulse technique, meaning what? You will transmit, the transmitter will transmit radio pulses in the direction of the target. Okay, in the radio pulse will strike the target and the same radio pulse at same frequency will come back at the transmitter. This is called operation or mechanism of primary radar. So the frequency at which you are transmitting the radio wave, that at that same frequency the radio wave gets reflected back. In case of secondary radar, the radio wave is transmitted at one particular frequency. Let's say 1030 megahertz. 1030 megahertz. Okay, it is 1030 megahertz, right? And it will reach the target. Let's say aircraft. After reaching the aircraft target, that frequency will reflect back from the target at a different frequency, 1090 megahertz. So the frequency at which the ground will send the radio wave will be 1030. The frequency at which it will receive that reflected radio wave will be 1090 megahertz. So 1030 and 1090 are different frequencies separated by 60 megahertz. So this is the operation of secondary radar. Okay, the frequency at which you transmit the wave will be different from the frequency at which you are receiving the reflected wave. So that is called secondary radar. In case of secondary radar, there are two objects required, materials. One on the ground, let's say ground interrogator. If the ground equipment is transmitting the radio wave, it will be called an interrogator, ground interrogator. And the object which is in the air, which is responding, okay, which is answering to this radio wave, will be called transponder. Okay, transponder. So this will be transponder in the air, a ground transmitter on the ground. Okay, it can be other way around also. In case of BME, we have transmitter or interrogator located in the air, atmosphere, and we have transponder located on the ground. Okay, so transponder can be in the air or it can be on the ground. Similarly, ground transmitter or interrogator can be in the air or it can be on the ground. So that is transponder interrogation. It is based on secondary radar. Phase comparison is VOR. It's not primary radar. Continuous wave transmission is radio altimeter. Okay, not primary radar. Next. Question 4. The main factor which determines the minimum range that can be measured by a pulse radar. So main factor. There may be a lot of factors, but out of them the main one which influences your minimum range is pulse length, amplitude, pulse repetition rate, frequency. So the correct option is option A. Pulse length determines the minimum range. Okay. And frequency determines your maximum range. Remember this. Amplitude is another definition, is a term which is associated with a radio wave. Basically, remember this in case they ask you for your RTR Viva. This is your radio wave. So this radio wave is called sine wave. There is amplitude. You can see there is positive amplitude. There is negative amplitude. Now what is amplitude? Amplitude is nothing but the maximum displacement of the radio wave. This radio wave, maximum displacement of the radio wave from the x-axis. Remember this. You can find a better definition also, but if anybody asks you amplitude, so it is maximum displacement of the radio wave from the x-axis, above the x-axis or below it, in quadrant first or quadrant number 4. So that is one thing. Next, question number 5. Ignoring pulse length, the maximum pulse repetition frequency that can be used by a primary radar facility to detect targets unambiguously without confusion to a range of 200 nautical miles is how much? So there is a formula. We all know that speed in case of radio wave or speed of light is equal to frequency into wavelength, right? Frequency into wavelength. So wavelength is nothing but distance, meter, will be equal to speed, meter per second, divided by frequency. Okay, frequency divided by frequency. So we can convert this formula. This is the basic formula. Speed equals to frequency into wavelength. Now in case of radar, what can we do is, in place of wavelength, I'm going to write range, which is a distance quantity. Speed, in place of speed, I'm writing small c, which is speed quantity, meter per second. Okay, divided by frequency. So I'm writing f, and I'm going to multiply this by 2. Okay, I'm going to put the value number 2 or value 2 in the denominator. That means I'm going to put half in the denominator. Why half? We always divide it by 2 because in case of primary radar, the transmitter is going to send radio pulses in the direction of the target. It will go to the target. This is distance x. It will come back, touch the target or reach the target, get reflected and come back at the transmitter. So the distance will be same, x. So the distance, the total distance traveled by the radio wave will be x one way, again x back two way. So it will be 2x, x plus x or x into x, x multiplied by 2 times, so 2x. Okay, but this is 2x distance traveled by the radio wave. But what we are most concerned about is that to find the distance of the target from the transmitter, that is only one way distance. This one way distance of the target from the transmitter. We are only concerned about that. We are not concerned about two-way distance. So that's why whatever distance we find out, that distance is going to get divided by 2. Okay, in order to eliminate this 2 quantity in the numerator, we are going to divide it by 2 so that we are left with only x. That is one way distance. So just remember, this is the formula. Range is equal to speed divided by f into 2. In case you do not want frequency in the equation, you want wavelength, the same formula can be rewritten as range is equal to c into wavelength divided by 2. Okay, and all the units will be SI units, standard units, meters, seconds. In place of microseconds, it will be seconds. In place of kilometers, nautical miles, it will be meter. Later on, at the final stage of a calculation, we can convert that into corresponding nautical miles, knots, microseconds, whatever. So remember this concept and remember this formula. Okay, so let's use the formula. The formula I'm going to use is range is equal to speed 2 into f. Now what is the range given to us? It's given 200 nautical miles. So 200 nautical mile is equal to speed of radio wave is 3 into 10 raised to 8. meter per second, right? Divide by 2 into f. F is what we have to find out. Frequency is what we have to find out. Now here there is nautical mile, here it's meter per second. So let's equate the units of left hand side and right hand sides. So let's convert 200 nautical mile into corresponding meter. So 200 nautical mile into 1.85 kilometers into 10 raised to 3 meter, that is 1000 meter. Okay, is going to be equal to your C divided by 2F. C divided by 2F. Just a second, I will use the new slide. Okay, so 200 nautical miles into 1.85 kilometers into 1000 meter equals to 3 into 10 raised to 8 meter per second divided by 2 into F. Cross multiply. F will be equal to 3 into 10 raised to 8 divided by 2 multiplied by that quantity, 200 into 1.85 into 10 raised to 3. Now cancellation, frequency will be equal to 3 into 10 raised to 3 divided by 2 into 2 into 1.85. So 4 into 1.85, 7.4. 3 into 10 raised to 3 divided by 7.4. So 3 divided by 7.4 is 0.405 something multiplied by 10 raised to 3. Okay, so frequency will be equal to 405 pulses per second. This is your final answer. 405 pulses per second. So the correct option here will be option number Charlie, 405. Next. The maximum range of a primary radar depends on what? Maximum range they are talking about. So maximum range is pulse recurrence frequency. Pulse length determines minimum range. I am saying it again. Frequency is number of pulses transmitted every second. Wavelength is the distance of one radio wave, a sine wave. So diagrammatically I can represent it. Okay, so this will be wavelength from here to here, wavelength. Okay. Next there will be another wave, again same wave progressing. So this is your wavelength. For any given circumstances, in order to double the effective range of a primary radar, the power output must be increased by a factor of what? Remember, in case of primary radar, in order to double the effective range, double the range, you will have to increase the power of your transmitter by a value of 4. By a value of 4. In case of secondary radar, the advantage of one advantage of secondary radar is this, that if you want to increase the range by twice, okay, if you want to double the range, you will have to increase the power of your transmitter by a value of 2, just 2. But in case of primary radar, it will be 4. Why is that? We all know that primary radar transmits a radio pulse in the direction of the target. Okay, a radio pulse. Let's say this is your transmitter. Here it's your target. It will transmit the radio wave in the direction of the target at, let's say, at frequency f, that same radio frequency f will get reflected from the target and come back at the transmitter. But in case of secondary radar, we use one particular frequency, let's say 1030 megahertz for transmission, and the wave that is reflected back at the transmitter is at another frequency 1090 megahertz. So the frequencies of the transmitted wave is different from the frequency of the wave getting reflected. Because of this difference in frequencies, the power required is much less than the power required by primary radar. Okay, so remember this why, or the reason why we need less power at secondary radar and more power at primary radar. It's because of this. In case of primary radar, the same frequency is used throughout that to and fro distance. But in case of secondary radar, one particular frequency is allotted for one-way distance. Another frequency is used for the return journey. So that's why the power required by secondary radar, okay, is much less than the power required by primary radar. Meaning, if I want to double my range, currently the range that I have is, let's say, 100 nautical mile. If I want to make it 200 nautical mile, I will have to increase the power of the transmitter by 4 times to achieve that double range. But in case of primary radar, in case of secondary radar, to achieve that double range, 100 miles to 200 miles, I will have to increase the power output of the transmitter by twice, only twice the amount. So that is one advantage. Okay. So at a given power, you get more range from the secondary radar compared to primary radar. Okay, that is another thing. Remember, so effective range of a primary radar, the power output must be increased by a factor of 4. Effective range in case of secondary radar, read the question carefully in exam. In that case, it will be 2. Okay. Next, the prime factor in determining the maximum unambiguous range of primary radar is what? Maximum range. So for maximum range will be determined by pulse recurrence rate or pulse recurrence frequency. Okay. Power output, size of parabolic receiver aerial. Okay, this two things, power output and size of parabolic receiver aerial, will determine beam width. We always need narrow beam width for resolution. Okay, for accurate resolution of the target. So power output and size of parabolic aerial will determine that. Height of the transmitter above the ground, right? So again, height of the transmitter above the ground and height of your aircraft. Since all radio waves are travel or follow the line of sight principle, that means the aircraft or the target must be in the range, okay, must be within the range of the transmitter, line of sight range. So height will also influence the factor, but the main factor determining maximum range is pulse recurrence frequency. Which of the following types of radar systems are most suited for short range operation? Okay, so short range operation. Primary continuous wave, centimetric pulse, millimetric pulse, secondary continuous wave. So the correct option here will be option Bravo, centimetric pulse. That means the pulses that you are transmitting are in the frequency band of 9 gigahertz, 10 gigahertz, 15, 17 gigahertz. So very, very high frequency, super high frequency. Okay, so super high frequencies will have a wavelength in terms of centimeters. And the super high frequency, the instruments using the super high frequencies are airborne weather radar, frequency band of 9 to 10 gigahertz. Then we have airport surface movement radar, frequency band 15 to 17 gigahertz. Now, airport surface movement radar is that radar which is used to locate the targets, to locate the positions, the movements of aircraft in the air at the airport. Okay, so because if there are large airports, which are large international airports, the ATC controller will not be able to see all aircraft from his tower balcony. So in case of, so for supervising and for supervision for accurate and proper surveillance, for safety reasons, we have this airport surface movement radar. So even if some aircraft or any parking area, apron, any part of the airport is away from the eye of an ATC controller, he can use his radar screen, that is airport surface movement radar, and on that radar he will get to know the positions of aircraft, their movements, be it aircraft, be it any other vehicle. Okay, all the information of the airport will be presented to him on his radar. So that is one advantage of airport surface movement radar. And since the ATC controller is only concerned about the airport area, the range of this radar need not be very great. It can be some 4 nautical miles, 4 to 5 nautical miles long. In case of airborne weather radar, similarly, we do not need maximum ranges, big, great ranges, because we are only concerned about weather which is going to be encountered in a flight path, the path that we are flying. Okay, so we are only concerned about that weather which is just in front of us that we are going to encounter. So 20-30 nautical miles is enough. So that's why airborne weather radar will also have centimetric pulse. Remember this. Next, question number 10. In which frequency band do most airborne weather radar and ground-based ATC radar systems operate? So frequency band is super high frequency. Okay. Airborne weather radar and ground-based ATC means we are talking about surface movement radar. So this systems will operate in the frequency band of super high frequency. Corresponding wavelength is centimeters. So remember that. Basically, all primary radar, all instruments working on primary radar will have frequencies starting from ultra high frequency band. So starting from that band, it can use frequencies from UHF band, SHF band, extremely high frequency band, depends. But this is the general super high frequency airborne weather radar and ATC radar. So yeah. Now I'll stop here. We will do the next 10 questions in the next video lecture. Till then, practice this first 10 questions from Keith Williams' Radar Theory chapter, write them down. Watch the video lecture in which I have marked important points from Basic Radar Principles Oxford book, and make good notes. Revise them every day, and this way you will remember the facts, understand the concepts, and you will enjoy learning radar, because radar is a big concept. There are systems working on this radar. There are different things that when you start flying, you will be actually using radar. So when you start your IFR flying, you will encounter many terms related to radar. So when you do this, that will become very easy to understand and implement the knowledge. So thank you for your time. I wish you all the best. Subscribe to this channel if you haven't yet, and please share this video with your friends. I'll see you in the next video lecture. All the best.